Assalamu alaikum students. Welcome to our last two combined sessions that are reserved for the revision purpose for the course Digital Logic Design. My name is Ali Rahman and this session is specifically designed for the students of BCS 3 and BCS 3D. In this session basically we will be reviewing our concepts, some of the concepts that we have learned in our theory sessions before our terminal examination. So lots of theories has been made. So after going through your theories, the session is arranged. So these two sessions basically cover those details which you have missed or which you have confusion regarding understanding the concepts. So these sessions basically totally focuses on the revision, and we would like to thank the authors of the book of the digital design with introduction to Verilog HTL, because all of our sessions were based on the book and the content were taken from the book and the slides itself. So at the ending note we would like to thank Mr. Morris and Michael. So to start with, lots of students have said me that to revise the mapping technique and to see if we can arrange a lecture in such a way that we can implement any combinational logic from scratch, starting from the Boolean function, then application of that Boolean function and simplification also, and also to see various options of the implementation. For example, if we have to implement that Boolean function by the decoders only, or we can implement that Boolean functions by multiplexers, or we can implement that Boolean functions by use of tristate case. So we will be focusing on an example that will cover all the aspects regarding the combinational logic design. So let us start our discussion by presenting a function. Basically, I would going to write a random function here, and for example, we've got a four literal function that is f of w x y and z, that is equivalent to or equals to in the terms of sum of main terms. For example, that is equivalent to, let me write some random terms here. For example, 0, 1, 3, 4, 6, 8, 12 and 15. So we have to implement that, and we will see how we'll implement that by using the primary gates as well as by using uh, the techniques that are used to simplify the following Boolean function and implement that by, again, and then we'll see how we'll implement that function by the decoders only, and then with multiplexers and then tristate case. So the first step which the student has to do is first of all to implement a truth table in order to see the relationship. But if you know the following terms and it's a four literal function, we can directly write those terms and we can directly convert it into the literals or the Boolean function in the form of literals. So for example, 0 is equivalent to 0, 0, 0, 0, and 1 is equivalent to 0, 0, 0, 1. 3 is equal to 0, 0, 1, 1. 4 is equal to 0, 1, 0, 0. 6 is equal to 0, 1, 1, 0. 8 is equal to 1, 0, 0, 0. 12 is equal to, or 12 equals to 1, 1 0 0, and 15 is 1 1 1 1 in binary form. So the first variable, this is basically the w, this is x, this is y, and this is z. Since the Boolean function, the sum of min terms contains those min terms that are producing one at the output, so uh, uh, we can write these in terms of literal as w prime, x prime, y prime, and z prime. Similarly, it is w prime, x prime, y prime, and z. The next term is w prime, x prime, y, and z. Similarly, the next term is w prime, x, y prime, z prime. And similarly, so on and so forth, we will represent this term, this term, this term, and this term. Once we have achieved the Boolean function in literal form, we can implement it by using the primary gate. So we just have to implement those expressions which we have obtained by using the primary gates, or we can say that we can implement by using the universal gates as well. So that thing is the next thing is we have to simply implement that function. As far as the simplification is concerned, if we have to use or we have to implement the function by using the minimum number of resources, what we have to do is we have to use those techniques that are used to simplify the expression. Now, either we can use Boolean algebra or we can use some mapping techniques, for example, K-map technique. So let us discuss the mapping technique here since we have studied that. So we have to construct a map of 4 variables here. So that is 0 0, this is 0 1, this is 1 1, and this is 1 0. Similarly for the columns as well, this is 0 0, this is 0 1, this is 1 1, and this is 1 0. And we have to place those min terms in the map. For example, min term number 0 is 1, min term number 1 is 1, min term number 3 is 1, min term number 6, that is 0 1 1 0. So 0 1 1 0, this is 1. Min term number 8 is 1, this is 1. Min term number 12 is 1, that is 1 1 0 0. Min term number 4 is 1, I think so. If I haven't missed that, yes, min term number 4 is 1, and min term number 15 is 1, that is this one. The rest of the terms, the rest of the cells are 0. So the next thing is we have to make pairs in order to simplify the expression. So here we can see that, let me change the color here. This is the first pair of 4 cells which we can make. This is the second pair we can make. This is the third pair which we can make here in this particular scenario. And this is the fourth pair, basically pair of 1 cell, because we don't have any shared element or sharing between that cell here with the same value. So let us extract the terms here right now. This term or this cell will produce the same term because we don't get any simplification from this term here. So it's W, X, Y and Z. Now coming to the next pair, this one. Since we can see that W and X are now changing for the pair, so it would be W prime X here, and as far as in a columns value is concerned, and as far as the values in the columns are concerned, if you see that the Y is changing within a pair, here for the first value Y is 0, and for the this cell Y is 1, but Z is not changing here and it's continuously 0 here, so we've got Z prime here. Now coming to the third pair, this one. W and X are not changing, so we are getting W prime and X prime here. Y is changing but Z is not changing, so we've got Z here, and we've dropped the Y from the term. And now coming to the last pair, this one of 4 cells. If we can see that W and X are changing, so we have dropped W and X, but Y and Z are not changing, so we've got Y prime and Z prime from this pair. So what we've got the expression here in a sum of products format. We've got these 4 terms, and now we can easily implement those 4 terms in a sum of products format, and we can see that the terms here are much more simplified and literals are also minimized here for each term, and so the resources are optimized here. Now let us implement that with the help of decoders. But before going to that, let us first draw the logic diagram of the set simplified Boolean function. So we've got an OR gate here at the output, and the output of this OR gate is F. And it contains 4 terms. The product term 1, 2, 3, and this is the fourth one. And we've got here the AND gates. This is the first AND gate, and the input of this AND gates are W prime, X prime, and Z. We can also represent that in order to avoid the mesh here or the mess here. As W prime, X prime, and Z being applied at this AND gate. The next AND gate will be W prime, X, and Z prime. The next AND gate will be Y prime and Z prime. This is Y prime and Z prime, and last AND gate will be W, X, Y, and Z. W, X, Y, and Z. Now let us see how we'll implement that with the use of decoders and some combinational gates only. So first of all, let's decide the requirement for the decoder in order to implement that function. Here is, since we've got the total number of min terms are It's a 4 variable system, so the decoder would be 4 to 16:9 decoder. That is 4 to 16:9 decoder. We've got 4 inputs: 1, 2, 3, and 4. W, X, Y, and Z, and we have to implement F here. We've got 16 outputs here, starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Since we have to represent our Boolean terms, we have to extract those main terms here, and we have to OR those terms here. So we have to use an OR gate. And this is F basically. Let me redraw it again. This is basically F. And the terms were 0, 1, 3, 4, 6, 8, 12, and 15. So the same Boolean function is implemented with the help of a decoder and OR gate only. Now let us go and try to implement it with multiplexers. So what we have to do is, let us first see the requirement and the size of the multiplexer that is required to implement that function. So we can implement the following Boolean function by using 8x1 multiplexer. And in our theory session, we have seen two different methods in order to implement that multiplexer here. So I'm just giving the example of one of the method. I'm going to use that. If you are comfortable in the other method, you can also use that. First of all, we have to implement a truth table, or you can implement the implementation table directly. So we've got W, X, Y, and Z. And we've got F here. So let us write the terms here. And the last term is 1 1 1 and 1. Since I am not getting an option to write the last term, just going to the menu. So 1 1 1 and 1. This is the last term. And the output of this multiplexer is 1 1 0 1 1 0 1 0 1 0 0 0 1 and 0 0 1. So what we have to do is we have to consider the three most significant inputs as a select line of a multiplexer, and the least significant bit is the implementation, which we have to implement that on the end users or the input lines. So we are making here the pairs for the similar wx, and wx and y. This is the first pair, this is the second pair, this is the third pair, this is the fourth pair, this is the fifth pair, that's the sixth pair, seventh pair, and last one, the eighth pair. The next thing is we have to compare the least significant input with the air. We have to compare these two within a pair. Here for the first pair f equals to 1, for the second pair f equals to z, for the third pair f equals to z prime, for the fourth pair f is also equals to z prime, for the fifth pair f is also equals to z prime, for the sixth pair f equals to 0, for the seventh pair f equals to z prime, and for the eighth pair f equals to z. Now let us draw the diagram here. Here we got f at the output of the multiplexer. This is 8 cross 1 mux. You can also use the standard symbolic representation for the multiplexer, which we have discussed in the course. So we've got 8 input lines, 1 2 3 4 5 and the 8th one, and we've got 3 select lines, 1 2 3. These are our select lines basically. We will connect W, X and Y with the select lines. and we've tried the value of the selection criteria in decimal here. So for the first one, we will connect it with plus 5 volts. In order to provide logic 1, so we have to provide logic 1 here for the first pair. The second one is Z. The third is Z prime. We can also have an inverter here from this line here. The fourth one is also Z prime. The fifth is also Z prime. The sixth is 0, so we would ground that. The seventh is Z prime again, and the eighth one is Z. So in this way we have implemented the set Boolean function by using multiplexers only. Now coming to our last session, that how we're going to implement that by using tri-state gates. So what we have to do is we have to implement basically the 8x1 multiplexer by tri-state gate, and since we have already implemented the set function by using multiplexers, we just have to make the interconnections here. So what we have to do is, first of all, we would going to use the 8 tri-state gates here. This is the first one. This is the second one. This is the third one. This is the fourth one, and so on and so forth. We've got the 4 tri-state gates. And we have to use a decoder here in order to enable or disable those gates. That is 3 to 8 line decoder. So W, X and Y will be applied at the decoder inputs. This is 3 to 8 line decoder. And these output of the decoder will be connected to the gate enabling and disabling mechanism. And so on and so forth. Let me draw the last one. This is basically F. So the first gate here will be connected to Z, if you remember the previous function, and the last one was also Z, and I hope so the remaining inputs of these gates are, for example, G prime here, G prime here, Z prime here, and so on and so forth. So in this way we can also implement any boolean function by using the twisted gates and decoders also. Well student, that was all for today's session. These two sessions, if you got any additional queries regarding some other topics, we can discuss those in our discussion sessions in this way. So best of luck for your exams. I hope so you will be able to perform well in your examination, and Allah Hafiz.